CMC webinar series, and thanks for joining us. My name is Marko Dragic, and today we are very pleased to jointly host this webinar with a team from NRC, Canada's National Research Council. So today's webinar is going to feature 3 talks about gallium nitride technology. We're going to discuss Foundry services, technology features, capabilities, and all this will be an opportunity for us to learn more about NRC's latest development efforts that are aimed at bringing us to the next generation gallium nitride technologies. For that, just a reminder that questions can be sent through the chat box that you can see on the screen. You can send them at any time, and we will try to address most of them at the very end of the webinar during the question and answer period. CMC provides the research infrastructure to the NDN, the network and ecosystem of researchers, students, collaborators, companies across Canada. In our microelectronics technology portfolio, access extensive design, make, and test infrastructure for a number of IC technology platforms that are suitable for a broad spectrum of applications. So in context, gallium nitride technology certainly has an important place in our portfolio due to its unique capabilities to address high power, high frequency requirements for electronics and wireless communication applications. See access to gallium nitride technology through collaboration with NRC, and I invite you to visit our website www.cmc.ca for more information about the technology, licensing, fabrication schedule, pricing, etc. Today is intended to help you learn more about NRC's gallium nitride technology, how this technology and the supporting design environment can meet your research requirements. So I'm going to hand it over to our first speaker, Christos Sarakinos, Client Relationship Lead for Gallium Nitride Program at NRC.
Thank you, Marko. Marko just mentioned my name is Christos Sarakinos, and I work with NRC. I'm going to give you an overview of our gallium nitride services. Just very briefly, looking at the next slide, use some of the areas that NRC operates in. Our program is out of the Information and Communication Technologies group, despite the fact that a lot of our end applications tend to be aerospace. If you're not familiar with the NRC, we're Canada's research and technology organization. We have about $1 billion budget, 4,000 employees, and we serve thousands of industrial clients annually. Moving on to the next slide. The structure of the slides that follow, I'm essentially going to be focusing very briefly on our technology leadership, our expertise in semiconductors, our electronic design automation, and the ease of export. The next slide. Here's some examples of the end applications. You'll notice that most of them focus on radar and SATCOM applications. As you all probably know, GaN-based HEMS and amplifier MEMICs offer higher RF output, lower consumption, and more portable devices, among other benefits. So Jennifer, who's going to be presenting immediately after me, is going to run you through our program, but just at a very high level, I wanted to show you that we have a characterized and stable process, breakdown voltages in excess of 100 volts. Our initial GaN500 process gets you from all the way through X bands, whereas if you want to hit the higher frequency bands, our imminent GaN150 process will allow you to hit Ku, K, and Ka bands. I'll point out that all of our processes are with through wafers, which, as you know, is critical in the microwave space. Slide. You see here, along the bottom, a picture of the team attached to our Foundry. And so really do have a wealth of knowledge and a wealth of expertise. Some of the systems that we offer is quick-turn prototyping, on-wafer DC RF probe, reliability studies, and we also have some pretty terrific failure analysis capabilities. Moving slide. In of electronic design automation, Tom G is going to be taking you through our PDK in detail. I have to point out that our PDK offers the functionality that you would expect from such a platform, has built-in device libraries, automated device layout, schematic capture. We have circuit simulation and design rule checking, and export is fairly straightforward. I'd like to talk to you about our Foundry. Move slide. See here a picture of our campus. We operate out of a 65,000 square foot facility running on 3- and 4-inch wafers, and we have 6-inch capable tools. And of course, Foundry is located in Ottawa, and so the processing itself is being done in Canada, which is exporting to European countries much straightforward than it would be if the processes were being done in the U.S. The fact that ITAR regulations and restrictions don't apply to us. I'll hand it over to Jennifer right now. Thanks, everyone.
Good. My name is Jennifer Bardwell, and I am the program leader for Gallium Nitride Electronics at NRC. I want to tell you about NRC's Canadian GaN Foundry today. I'm going to be talking a little bit about the GaN500 version 3 Design Kit, which we've just released, and I'm going to be giving you a preview of the GaN150 Design Kit, which operates at 0.15 microns. I've already heard from Christos, who's described our Foundry service to you. On the slide, you can see our roadmap. In July 2014, we released GaN500 version 2, a design kit at 0.5 microns. And since then, we've just recently replaced that with GaN500 version 3, again at 0.5 microns, operating at C and X bands, and giving output powers of 5 watts per millimeter. The big thing about this new version of the design kit is that it includes through wafer vias. Shortly, we'll be releasing a version of GaN150. This is aimed at KU and K bands, and eventually we'll be expanding into KA band as well. It also has through wafer vias, and the output power, as measured at somewhat lower frequencies, is 7 watts per millimeter. In 2016, we will be releasing an enhancement mode GaN500 Design Kit. Again, this will be aimed at C and X bands, but enhancement mode devices operate in normally off operation, which provides some advantages for the designer. In mid-2017, we will be releasing the whole ball of wax, an integrated enhancement depletion mode GaN150 Design Kit. This is going to be a very interesting development because it will allow for designers to make digital type devices in gallium nitride. Let's start with what's new in GaN500 version 3. The things that I've underlined on this slide are going to be discussed further in the talk. We've added the Angelov transistor model in addition to the root model we already had with GaN500 version 2. Increased the second metal interconnect thickness 3 microns from 1 micron. And likewise, we've also increased the capacitor dielectric thickness from 100 to 300 nanometers. This is to enable breakdown voltages of greater than 180 volts. Importantly, we've introduced through wafer vias in order to allow the use of microstrip lines as well as coplanar waveguides. In addition, we've also updated the DRC rules, we've added more information on multi-project wafer runs, and we've removed support for ADS 2009. Talk about the Angelov model a little bit. This is a model that was done for us by Modelithics, and it includes thermal effects, so it has a little bit more flexibility than the root model. On the left-hand side of this slide, you can see the output current of the device, both in red from the model and in blue, the measured data. On the right-hand side of the slide, you can see the temperature effect as captured by the model. This is the drain current on a device as a function of the gate source, voltage, and you can see that there is a distinct change in the performance between 25 degrees and 85 degrees, which is well captured by the model. Slide, we see some load pull results, which were also obtained as part of this modeling. On the left-hand side, we have a validation of the load pull, both the power tuning and the efficiency tuning. On the right side, we show the power and transducer gain, and power added efficiency. as a function of the input power. On the upper right side of this diagram, you can see that we obtain a maximum output power of approximately 36 dBm, and this corresponds to about 5 watts per millimeter for this size of device, which is 2 by 250 microns. We've also increased the second metal interconnect thickness. This is required for performance at high frequency and high power. The process has been established and is in production, and excellent yields have been obtained. Looking at this scanning electron micrograph, you can see from the left-hand side 1 micron of the first metal interconnect, 1 Me, and overlaid on top of that is 3 microns of 2 Me. As we move towards the right side, you can see the 2 Me is forming an air bridge here. This is necessary for proper functioning of capacitors and inductors, and this is, of course, fully implemented. I want to point out the extremely small wing that is on the side of the thick 2 Me. This is important for high voltage operation. Found that we had to also increase the thickness of the capacitors in order to increase the breakdown voltage of the overall circuits. I'll show some examples of the testing that was done to determine the optimum capacitor thickness so that these devices will be, circuits will be useful at high voltages. On the upper left, we see a single IV curve for a capacitor. And you can see that this particular one is breaking down in excess of 250 volts. On the upper right, you can see the fractional failure plot for 50 devices mapped over the entire wafer. And over the entire wafer, only one device failed at 200 volts. The rest of them were in excess of 250. These types of measurements have been repeated for different sizes of capacitors and for different sweep rates of the applied voltage. And this enables us to calculate the lifetime of these capacitors at the operating voltage of 40 volts, and it's a very, very long lifetime. As mentioned, we've also implemented through-wafer vias. On the upper left of this slide, we see an optical micrograph of a device under test, and right below that, you see the GDS2 file corresponding to that layout. Circular, the lower left, are the white circles at the left, and in the image are the actual through-wafer vias. Just a little bit to the right of the diagram, the GDS2 file, we see coplanar waveguide device, the same size of device, but implemented as a coplanar waveguide structure, and this is, of course, still supported by the PDK. Right-hand side, we see some mapping of entire wafers where the short pad and the short via has been mapped, and we have 100% yield of the vias across this wafer. Now to giving you a short preview of the GaN150, which is expected to be released within the next couple of months. A design kit that's been optimized for high breakdown voltage. We expect better frequency performance will be an option in GaN150 version 2. However, this will come at the expense of some of the breakdown voltage. This particular design kit, the one we're releasing shortly, includes gain of greater than 10 dB for up to 25 gigahertz for smaller devices only, and it does, of course, include through-wafer vias as well. The figure shows the FT and Fmax response for a 2 by 100 coplanar waveguide device operating at a drain voltage of 30 volts. And you can see that the FT and Fmax are quite large for this device. There's the load pull measured only at 7 gigahertz for a 2 by 50 microstrip device. You can see that the output power has been measured as a function of gamma, and that the best output power is obtained at 0.8 gamma for this particular case. And the type of plot enables you to calculate the output power of 7 watts per millimeter. We've run an extensive series of RF measurements on these wafers, showing the gain as a function of frequency. So 5, 10, 15, etc., up to 35 gigahertz. We've measured a bunch of different styles, style A and B for microstrip type devices, and some coplanar guide devices with various numbers of gates and various total gate widths. You can see for the smallest device measured, style B with 4 gates and 40 microns gate width, we're obtaining gain in excess of 10 at 35 gigahertz. The devices, of course, are showing somewhat smaller gains at that frequency, and so one has to bear this in mind when designing devices for extremely high frequency performance. We also obtained very good stability and breakdown voltage for this process. On the slide, the pink curves show the stability measurements. These were mapped over an entire wafer, and they show the gate current density as a function of time while the device is under stress at 50 volts on the drain source and minus 10 on the gate. That decreases monotonically over the 1,000 seconds, which is an indication of the stability of the devices. On the lower right, we see the gate current density again as a function of the drain source voltage. This is a breakdown voltage measurement in pinch-off while the gate is being held in pinch-off at minus 5.5 volts. The curve shows that the breakdown starts about 200 volts for most of the devices on this wafer and about 150 volts for some of the devices. This is a very high breakdown voltage of 4.15 micron technology. In conclusion, we've released GaN500 version 3. It has lots of new features and much better performance, and we are, of course, going to be adding more features in revisions to come. GaN150 is coming soon. It's a high voltage Ku and K-band PDK for very good performance at those frequencies. And as mentioned, high frequencies will be addressed in upcoming versions of GaN150. I'd like to thank you for your attention, and I'd encourage you to contact us at gan@nrc.ca.
In this part of the presentation, I'm going to demonstrate NRC's GaN500v3 Design Kit. Currently, it only supports Keysight ADS for version 2011 onwards. The design kit was installed in ADS. One can see the GaN500v3 library in schematic window and layout window. Both are all listed component palette in schematic and layout. I will brief introduction to some components in the library in the later slides. Three HVAC components, all are the signal nonlinear models. The first one, named as GaN500 FET, is a rotor model with fixed unit gates with facing and a fixed number of fingers. The second, GaN-S-FET, is still a rotor model, but it scales with unit gate width. Gate width should be with 120 micron to 250 microns. It only supports two-finger devices. The second one is the GaN-A-FET is an Angelov model. It's a scalable model with the unit gate width. It might be within 20 micron to 200 micron. Supports two-finger devices. So you know, Angelov model into account the scaling effect. From GaN500v, we have introduced through wafer vias, so microstrip lines can be used for circuit design. For 500v3 components such as microstrip line, CPW, taper, cross, and etc., use one more parameter to select, that is metal layer. You have three choices: one only, that will have 1 micron thickness gold, or 2 only, that will have 3 micron gold, and ME plus 2ME, that you will get 4 microns in 2 centimeters. Please note, substrate is already incorporated into all these components. Semiconductor in GaN500v3 is the standard ADS built-in model. The substrate is already incorporated into the model. With respect to the minimum width and spacing, is 5 micron. The B via is the true wafer via on GaN500 Design Kit. The hole size is fixed at 15 micron, but you can put multiple vias holes on the same pad. The number of holes is determined automatically from the pad width W that you entered. The GaN500 encode, its component exists only in the schematic. And these components contain all models implemented in the GaN500v3 Design Kit. So these components must be based on any schematic which contains any GaN500v3 components. Just as I said, it includes the models for all the GaN500v3 library. So it's placed only in schematic. A little bit for the use of GaN500v3. The first is you to respect the design rules as listed in the design manual and use the DRC check tools implemented in the ADS. The components in the library to GaN layout, specs don't be too creative. One is recommended maximum bias voltage is 40 volts. All must have the same orientation on the entire tile. This will not be checked by the DRC rule checker implemented in ADS. Here on the left is with all these transistors having horizontal gates. But on the right, some of the transistors have horizontal gate and some of it have voltage that will not be accepted. I will follow illustrate the use of GaN500v3 PDK ADS. Thank you very much.
small glitch in our audio system, so apologies for this. So thanks very much, Christos, Jennifer, and Tong Ji. Right now we are going to open the floor for questions. And if you have any question, please use the chat line box that you can see on the screen. During presentations, we received the first question from Liang Zhu. And the question is if there is a maximum width for ME and 2ME in the design kit.
Answer that question, Marco?
Certainly, Jennifer, if you can address that.
There is no maximum width for the interconnect metal.
Okay. So we go to the next question that was sent also through the line. It relates to the introduction of the GaN150 node. What is the timeline for this technology to be introduced?
Well, we're finalizing the timelines, but we are planning on releasing it within the first quarter of 2015, March at the very latest.
Okay. Question is, have you characterized the memory effects for gallium nitride technology?
I understand the question. You mean used as a memory device, or mean do they have a memory embedded in the devices? I guess the person is asking about current collapse.
There are any memory effects with this? So, characterize memory effects for your process.
If the Angelov model could be there.
The answer is that the Angelov model may have included some memory effects.
And that we received is what is the typical fab lead time for the technology, for the tape out?
So once we receive the finalized designs, the cycle time is somewhere around 15 weeks.
Maybe I will add to this that on a CNC side, if there is some packaging requirements that may add more weeks, but in general, that's the timeline that one can expect to receive the check.
It makes sense to talk about the scheduling of CNC runs.
Certainly, we can talk about this. Gallium Nitride 500 is on our schedule. We have run every 2 months. The next tape out time is May 13th. And application for submission is March 10th. So I invite everyone to visit our fab schedule on cmc.ca, and more information can be found over there. We also receive another question that is what is expected in certain loss for a simple switch at 20 gigahertz and also at 30 gigahertz with gallium nitride 150. Someone from NRC team would be able to comment on this.
Depends on your design, right? Depends on the transistor you use or the configurations, right?
So Marco is that it's design dependent.
Okay, thank you. Another question relates to VS. What is the minimum spacing for VS?
Minimum spacing for VS. Spacing VS is part of the design rule. You find that in the design manual. I'll have to just look it up for you, so it'll just take a second here.
the meantime, I'm going back to the previous question that was received. We got a little bit more clarification. So the question about expected insertion loss for switch 20 and 30 gigahertz with NR150 relates to a simple switch structure. So I'm not sure if you would be able to provide any more details. But,
you can check on this one.
So the question is about expected resistance states on state with nitride 150 and more information about this.
Mark, what's the question, please?
So what is expected resistance for on-state switch with gallium nitride 150?
We're looking to characterize that right now. We don't have that data at this point.
Okay. So that's still open. If you have more questions about either gallium nitride 500 or gallium nitride 150, please use the chat line there.
Yeah, about the spacing between the two through wafer vias. The minimum allowed spacing is 65 microns from layer 14, which is the extra wafer via layer, right? From layer edge to edge.
Thank you, Jennifer.
And I'd like to add that the design manual is fairly comprehensive. It's 77 pages long. It has answers to that question and countless others. So we'd encourage listeners to download the design kit as well as the design manual.
Thanks. For a minute or so, if there are more questions. It's also mentioned that the slides and recording will be available through CMC website. If you further questions, contact us at any point of time. The question that just arrived is if there is any other than TFRs, such as MESA.
If the TFRs, thin film resistors, that's it?
That is right.
Yeah, thin film resistors embedded into the design kit.
So one more question relates to the previous generation of gallium nitride 500 technology and specifically refers to V2. The next gallium nitride 500, should we use the newest version V3 or we still could use V2? So
the answer to that is that we won't be offering GaN500 version 2 anymore. The differences between the two of them are really only that the capacitor dielectric is much thicker in GaN500 version 3, and this does make it necessary to make the capacitors geometrically much larger than in the previous version. We still offer coplanar waveguide devices in GaN500 version 3. The extra metal thickness that's available in GaN500 version 3 just really improves the performance slightly. It doesn't change the electrical piece of the transistors very much. So the short answer is no, we're not offering GaN500 version 2 anymore, but you're still free to do coplanar waveguide designs, albeit with larger capacitors, well, quite a bit larger capacitors in GaN500 version
That's clear. Questions here, so I guess we are going to close this webinar. So I would like once more to thank everyone for your participation. Thanks to the NRC team for a great presentation. If you have any further question, please feel free to contact us at any time.
Feel free to contact us as well at gan@nrc.ca. Thank you from our end too. Thank you, Marco.
Everyone.
Everyone, have a great day.